All right, so we are talking about chapter 24 to 24, capacitance, dielectrics, and electric energy storage. I think yesterday we talked about capacitance and we saw some problems how to calculate capacitance for like a spherical shell, cylindrical shell, two lines. And we said parallel capacitors have an equivalent capacitor as a sum, whereas like serial capacitors have like an equivalent sum, inverse of equivalent capacitance is like inverse of individual capacitances. We solved some problems. We talk about electric energy storage. Electric energy stored in a capacitor is given with either of these, whichever you like. It's like 1/2 C times Q squared, or by using this formula over and over again, you can convert it to this form or to this form, okay? And we said we could convert that electric energy to a form purely written in terms of electric field. And from that, we found that electric field, electric energy density is given by the square of the electric field. We solved some problems. We talk about dielectrics. And I think today I can solve some suggested problems. All right, this is the first suggested problem in your book. A large metal sheet of thickness L is placed between and parallel to the plates of parallel plate capacitor of figure 4. So it does not touch the plates and extends beyond their edges. A, what is now the net capacitance in terms of A, D, and L? And B, if L is equal to 0.40 D, by what factor does the capacitance change when the sheet is inserted? Okay, I think I can do that. So it's given A and D and L, everything is known. So I can calculate the capacitance without the without the metal sheet. And it is what? It's purely geometrical, right? It's like epsilon naught area divided by the distance between the plates. So it's something like that. Right, this guy has some electric field. The total distance is D. And we know how to calculate that, right? Now I insert, let's say, a metal sheet like this. Okay, and its thickness is, I think, given L. Now I need to calculate what? Now I need to calculate C. Okay, so let's say I have plus Q here. I have minus Q here. What's the electric field inside the metal sheet? Electric field inside is 0, right? Yes. And I know if electric field is 0, this guy should have minus Q. This guy should have plus Q, but doesn't matter. So capacitance is given by total charge divided by voltage difference. And voltage difference is something like E dot dl from, like, say, from 0 to D, from 0 to D, and electric field is sigma over epsilon naught. And sigma is equal to charge divided by area. All right, then I can calculate V. This V has two contributions. So electric field here is non-zero, so there will be a V contribution to this integral. Electric field here is 0, so there will be 0 contribution. And electric field here is again the same thing, so there will be a non-zero contribution. So overall, V is going to be equal to E, which is sigma divided by epsilon naught, times total distance minus this little distance, which is d minus L. Now I can put this in the equation for C, then C is equal to, Q is equal to what? Q is equal to sigma times area, divide this thing by sigma divided by epsilon naught, d minus L, right? As a result, I have something like epsilon naught area divided by d minus L. Okay, this is A. So B, if L is equal to 0.4 D, then D minus L is equal to, all right, maybe I can do it this way, D times, actually I can even calculate, 0.6 D, then C is going to be equal to epsilon naught A divided by 0.6 D. This is approximately what? 1.6 times epsilon 0 A over D, 1.6 times bigger. All right, next question. 3 conducting plates, each of area A, are connected as shown. And the first question is, are the 2 capacitors thus formed connected in series or parallel? This arrangement is a series or parallel. B, determine C as a function of D1, D2, and A, and assume D1 plus D2 is much less than the dimension of the plates. And C, the middle plate can be moved, this guy can be moved, I guess, up and down, changing the values of D1 and D2. So as to vary the capacitance, what are the minimum and maximum values of net capacitance? All right, let me start. So let me first write, like put the gaps and then complete the picture. So the first gap is something like that. And this one is D1. So now this guy, I write it almost like this is like a medal. What does that mean? It's like something like that, right? And the second gap, let's put the second one. And this is D2. And it seems like there's like a connection from here to here, something like that. And this is V. And now I need to connect this guy to this guy, right? Now I think it's a little easier to see. So my question is, these 2 guys, are they parallel or series? Parallel, right? You can just cut this guy here and put it here and connect it like this. So you have like a parallel by definition connection. So A, parallel. So B, let's move on with B. Determine C as a function of D1, D2, and A. So these are like capacitors in parallel. Let's call this one C1 and C2. And C, like equivalent, if they are parallel, we know it's like C1 plus C2. But C1 and C2 are purely geometrical in this case. They are like epsilon 0. The area is given A, and the distance is D1 plus epsilon 0 area of the other one and the distance of the other one, and that's it. And that's equal to epsilon 0 A 1 over D1 plus 1 over D2. And we, of course, like assume they are like parallel plates. That's like for us to be able to write this, I think they have to, D1 and D2 has to be very small, right? In compared to area. And now the last one, C, it says D1, okay, this guy can be moved freely, but I think what they mean is like D1 plus D2 is fixed, right? You can move this up or down, but the sum of D1 and D2 will be fixed. So let's put this in. Let's call D is equal to D1 plus D2, and let's call D1 is equal to X, then D2 is equal to D minus X, right? And now I can put this in our formula, then C equivalent is equal to, so not area, the first one is 1 over X, plus the second one is 1 over D minus X. So what are the maximum and minimum net capacitance? I think usual way is you can find the minimum of this thing, but we can do it graphically for this case. I can plot it as a function of X. So let this be X. So this is 0. So X changes between 0 and D is D1 plus D2. So if X goes to 0, this thing blows up because 1 over 0 is infinity. So I have something like this. And if X goes to D, the second guy blows up. So I have something inverted, something like that, right? Obviously, C equivalent max is infinity because I can take X as small as I want and it's going to blow up. And the minimum should be here because you can tell graphically, it's like where it should be. And this thing, I think, seems to be in the middle, D over 2. So if you put that C equivalent, min is equal to what? So this is D over 2, 1 over D over 2 times 2, 4 over D, it's something like this, 4 times epsilon naught A over, and D, let's remind what D was. D was D1 plus D2. So it's like D1 plus D2, right? So if you write it, I'll read it, okay? I'll continue now. I'm not sure if maybe you are disconnected. So the next question. Suppose one plate of a parallel plate capacitor is tilted, like they're normally like this. This guy is tilted. So it makes an angle theta. It makes, actually, they say, a small angle theta with the other plate, as shown in the figure. Determine a formula for the capacitance C in terms of A, D, and theta, where A is the area of each plate and theta is small. And assume the plates are square. And the hint, imagine the capacitors as many infinitesimal capacitors in parallel. So I will use the hint as they suggest, okay? They said, imagine capacitor as many infinitesimal capacitors in parallel. And I believe what they mean is like these little things are like one capacitor, this one is another one, this guy is another one. And these little squares, actually they are like extended, right? Like this. These little things, I'll take like small capacitors and I'll add them. So let me write 1. So let's write DC is equal to. I need to label a little bit stuff here. So let's call this L, actually let's call it Y. And this little chunk here is dy. And the distance, okay, this is like a little capacitor and it speaks to this other guy here. And I need to know the distance. So this guy is given D. So this guy, I need to find something for this. And I can write it in terms of theta. So this guy, I know y. So this guy, I can use tangent theta is equal to this question mark divided by y. Then this question mark is equal to y times tangent theta. And also let's do this small angle approximation, y times theta. Okay. So now let me write this. This thing is like epsilon naught. The area is dy times, okay, this thing is like, let's call it L by L, dy times L, and this is equal to area. And the little area divided by the distance is d plus y theta. And now I know the capacitors in parallel are like summed up, which is nice. So C equivalent is sum of all these little chunks, which is DC, which is equal to E L, so this is dy divided by d plus y times theta. And my limits are going from y is equal to 0 to y is equal to L. I think this integral we can take. It looks like a logarithm. So this is E L. So this is ln d plus y theta, right? If I take the derivative of ln, I have 1 over d plus y theta, and derivative of y of theta is theta. To compensate that, I have to put like a theta here, and that's good. And I need to put the limits. It's going from 0 to L, and this thing is equal to epsilon 0 L over theta ln d plus L theta divided by d, or we can write it a little bit like nicely, 1 plus something like that. Okay, and that's it. Right? Maybe actually I can simplify this, right? So this ln 1 plus x is equal to approximately x. Then C equivalent should be equal to epsilon naught L over theta times L theta over d, and this is equal to epsilon. Okay, seems like in the lowest order it doesn't change, so EA over, okay, so that's a good thing. So the EA over D, that's what we know it should be. So I will take the next order term. I think if you look at the logarithms, I think plus or minus. Does anybody remember logarithm? Like I think it's 1 over 2 x squared. But it could be plus, I'm not sure. I think you should check this sign. I think it is minus, but it could be plus. And if that's the case, I have a second term here, epsilon naught L over theta 1/2 L square theta square over d squared. So the second thing becomes minus epsilon naught A over d times, okay, let's write everything else that's left. 1/2, okay, this guy will cancel with this guy, L theta over d, something like that. Okay. Yes, and L is I defined here, right? I mean, I just called one L, the other one is L. So If you don't like it, take the square root. It's okay. Next, the next is like this. I think is this the last one? Yes, this is the last one. A slab of width d and dielectric constant k is inserted at distance x into the space between the square parallel plates of side L of a capacitor as shown in the figure. And you'd like to determine as a function of x, A, the capacitance, B, the energy stored if the potential difference is V naught, and C, magnitude and direction of the force exerted on the slab. Okay. So I think I can think of this thing as like two, right? Two capacitors. One is this guy, the other is this guy, and they are connected in parallel. And parallel capacitors are wonderful things because we just sum them up. So C equivalent, the first one is epsilon naught. Area is equal to, okay, this area, if this is x, the other one is L minus x, and the other dimension is also L. So area is L times L minus x, and divide this thing by the distance d. And the second thing is exactly the same. So epsilon naught L times x divided by, so the first thing is area divided by d. But if you remember, I think we said the only thing that will change for a capacitor with dielectric is like a constant here, kappa, right? I think I'm pretty sure we talked about this, but let me show you that page. Somewhere, I think here, right? We said you can do this kind of hypothetical experiment, and if you insert it, like it's like either you can think of constant V or constant Q, but at the end what changes is like capacitance is multiplied with a constant kappa, and this kappa is something bigger than 1. That's what we need to know. So let's come back to this problem. So that's what it is, and I think determined as a function of x, that's it, right? That's all we need to know. I can like try to look at this equation and write it a little bit more compact. So it's going to be like what? Let me take some common factors. It's going to be epsilon naught L, actually let me take L square outside and divide it by D, and it's going to be equal to 1 L squared minus x over L, and lastly plus k x over L. Actually, let's write these two things together. So I'll just write this as k minus 1 x over L. Now I can pull this guy here and close the parenthesis. And this is a plus. Any objections? Now this is the capacitance. I need to find energy. So A and B. And for energy, what kind of energy? It's like a fixed potential difference, right? Like potential V naught is fixed. So I can use, let's see, which equation can I use? So we said, okay, if we forget the energy, how do we derive? I kind of forgot it, but I don't want to go back and look. So the work you do is equal to dq times V, and C is equal to what? C is equal to total charge divided by V, and V is equal to then it's equal to dq. Okay, this is q dq. So V is equal to Q over C. So this is Q over C. If you integrate, this is total energy. U is equal to 1/2 C Q squared. So this one is not good for me because I have a fixed potential. So let me try to rearrange this. So I put Q over C. Okay, this is equal to 1/2 C squared Q squared divided by, okay, multiplied by C, but Q over C is equal to V, so it's equal to 1/2 C V squared. This one is good because I calculated C and V is V not 0, so I've got everything. So energy should be equal to, okay, use this one. U is equal to 1/2 C V squared. So I can clean this. Okay, now I also clean this. Now let's put these numbers. C, I just calculated. So U is equal to 1/2 C, I just calculated E L squared over D. And this thing is 1 plus K minus 1 X over L. So I wrote C, I wrote 1/2, and last thing is V naught squared, right? Let's see what if they are asking anything. Energy stored if the potential difference. Okay, that's it, right? And finally, see magnitude and direction of the force exerted on a slab. A, B, and C. Force on slab. How do you write it? Okay, slab. How do I find it? How can I write the force? So how, like, why would there be a force? It's the energy difference. But like, I'm not sure why would there be a force here. So I think I would like to take you to first semester again. Like, given the potential, right? U sum X, how do you get force? Do you remember? For a given U of X, what is the force? Does anybody remember how to get the force from the potential? Exactly, right? Thank you. Yes. It's like minus du dx. Can we use this? Can I use this? Any objections to using this formula? Of course we can use it, right? This for this one, like I will use it. And force is equal to minus du dx is equal to, let's exercise derivative, 1/2 epsilon naught L squared over D times V0 squared. The only derivative is inside, and it should be equal to K minus 1 over L. And there's an overall minus like this. I think that I don't need these square brackets. Oops. Let me clean this. And let me push this a little bit. And now I need to determine the sign of this thing, because the sign will determine the direction. So the gradient, so this is like we said, if you remember, this is the gradient along X. And if you want to find the force along Y, you can do du, dy, and so on. But the sign is important. This tells you if you're like, if the sign is positive, you have like this way. If the sign is negative, you have this way of force. And I need to determine the sign of this thing. So this thing is positive, positive. These two guys are positive. This is positive. L is definitely positive. And kappa is the dielectric constant, and its minimum value is 1 in air or in vacuum. So this is also positive. So this whole thing is less than 0. So the force acts to left. Okay, this way. It kind of sucks the slab in to get it here, okay?